Well, the first bit of news is exam 1 is a week from today. Yay. Yeah. So that is the 9th. And the topics for that are going to be everything up through particle kinematics in a non-rotating coordinate system. I'll leave that off, but that's all we've done so far. And so please bring questions on Wednesday if you have any. And, any homework problems you want to go over on Wednesday, I'd be happy to do that. Anybody have any questions about the test? Yes.
Since Wednesday's the last class till the test, are we going to be going over new material that won't be on the test?
Yeah, if there's no more questions or anything, then I'll just keep going on with new stuff. Okay. I mean, if we run out of questions and still have time, then we'll go on to new stuff, but it won't be on the test.
Like kind of a review day for it?
It's, well, yeah, right. Okay, so you didn't ask this, but I often get asked, like, do I ever do like sort of review summaries for tests or whatever? And I don't ever do that. I mean, I feel like I try to boil it down in class as much as I can, and then I think you should be responsible for the stuff I say in class, and the exams are just based on problems, so the exams are mostly just like the daily assigned problems. Yep.
And then is there going to be like an exam sheet going over like all the topics that we should know?
No, yeah, right. There's not anything like that. Like it's just everything in your notes, everything in your assigned problems up through particle kinematics. Yep. Any other questions?
Yeah, like on Wednesday, can we go over to like some of the first
Sure.
problems that we
Yeah, I'd be happy to do that. And then I'll give you your first weekly assignment like sometime before the test. So anyway, so look for that too. But and you'll have like a week to work on that, so you don't have to work on it at all before the exam if you don't want, but it'll be there. Okay, so the first homework question I got was on number 13 from particle kinematics. You have an object dropped inside a moving vehicle. A camera inside the vehicle measures an acceleration. What's the acceleration of the vehicle? This is pretty similar to an example problem we did, but different numbers. So I'm going to think of it as, I'm going to think of O as the object. V is the vehicle. And G is the ground. And I'm going to set up we're talking about acceleration, so I'm going to use the acceleration equations. I'm going to set it up as the acceleration of the object relative to the ground is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground. And then take a second and make sure that if you multiply these fractions on the right, they come out to equal the fraction on the left. Yes?
Yeah, so what I'm trouble is with like coming up with the formula.
Okay, yeah. Okay, so there's two ways to do it. One is it's very common in these problems that there'll be a thing that's moving. That'll be the particle or the object or whatever. There'll be a vehicle, like sort of an intermediate coordinate system, and then there'll be the ground coordinate system. Okay.
So we never like consider the camera.
The camera is always mounted to something. So in this case, the camera that it mentions is the vehicle. You know, it's stuck to the vehicle. Right.
Okay.
Exactly. And so if you have an object that's moving and a vehicle of some kind and a ground system, then this order always works. The object relative to the ground is equal to. So that's one way to think of it. The other way to think of it is to just figure out what you're trying to calculate, put that by itself, put the other two things in any order you want, and then use the flipping subscripts flips the sign rule to get the signs that work. Yep.
So when we're considering these types of problems, like I think problem 12 was with the plane in the air.
Mhm.
When we're considering like the ground, is that always like the earth, the surface of the earth, or is that like the ground is like the floor of like the airport?
Oh, I got you. Yes, it's always the Earth, or like the most zoomed out you can be. And by the way, I guess now is as good a time as any to mention for the first time. I'm sure you've all, it's come up to all of you at some point that the Earth is not an inertial coordinate system. And so in a lot of these problems, I'm sort of glossing over the fact that a camera mounted to the Earth really is not an inertial coordinate system, but it's really close to one. And when we talk about the effect, the reason it's not an inertial coordinate system, the biggest reason is that it's rotating. Okay. And coordinate systems that are rotating are not inertial. But how far from an inertial coordinate system something is depends on its angular velocity, its angular speed, basically. And if you think about the angular speed of the Earth, it's a very, very small number, you know? So it's doing one full revolution every 24 hours. So one revolution is 2 pi radians. And then every 24 hours, if we're putting it in radians per second to get an angular speed that we're used to, that would be so that gives an angular speed of 0.000073 radians per second. And since that's so small, it doesn't have a big effect. Big enough that if you have very sensitive measurement equipment, you can see it. But if you don't have very precise, very accurate measurement equipment, you just don't even notice it. So we're going to, most of the time, until we start talking about rotating coordinate systems, we're going to assume that the Earth is inertial, even though it's not quite. Okay. So yes, ground always means Earth. That's the too long didn't read version. Okay, so now we have this. The acceleration of the object relative to the ground. This thing is in free fall, so this is going to be 0, negative 9.81. The acceleration of the object relative to the vehicle is this measured acceleration. So negative 5, negative 11.5. And then we're trying to calculate the acceleration of the vehicle relative to the ground. And so do the algebra, and you get 0, negative 9.81, minus negative 5, negative 11.5. Yes.
If we rearrange it with the A's at the beginning,
Mhm.
if I do I know that I'm looking for A, V over G.
Yeah.
And if I do A O over G minus A O over V, those fractions don't work out to be a.
Yes, correct. Okay, so let's go through it that way and see how you get the same answer. So okay, well, this is the answer, first of all. So we can tell that compared to the Earth, the vehicle has an acceleration of 5 in the positive x, 1.69 in the positive y. Okay, another way that we could do this. We could say, we know we want the acceleration of the vehicle relative to the ground. Okay. And the other stuff we want is, we know we have an expression for, like we can just put in the things that were given. We know we have the acceleration of the object relative to the ground because it's free fall. And we're given I don't really know the notation I'm going to use here because this, let's do this. These aren't equal yet, but we want them to be. Acceleration of the origin of the object relative to the ground plus the acceleration of the object relative to the vehicle. Okay. So I'm putting those two in there like that because those are the two things that we're given or that we know. But if you look at this, if you think of this as, V over G is not equal to O over G times O over V. So to make this multiplication equation work, all we have to do is flip. We want the reciprocal of O over V, And so that's when I'm going to go. So in order to flip the subscripts of the acceleration of the object relative to the vehicle, I'm going to multiply the whole thing by -1. Okay, that's in your notes from a couple days ago. So this is equal to this minus the acceleration of O over V.
We could also get by rearranging the original expression.
Exactly, and so this is the same expression that we have, O over, same expression that we have up here. Those two approaches both work perfectly fine. To me, I think it's a little simpler to just always think like there's a ground and there's an intermediate coordinate system, often a vehicle of some kind, and there's an object that you're tracking, and just put them in this order.
And that would always work.
The one below?
No, that one, the first one.
Yeah, as long as you have, there might be cases where it's not so clear what's your intermediate coordinate system and stuff, maybe. But I think when I do these problems, that's how I always think about it. So you can make it work in your head always.
But the fraction canceling rule doesn't work with the second one.
Well, yeah, so then anytime the fraction canceling rule doesn't work, you have to make it work by, so I guess here's the step that I kind of skipped here is that it's equal to plus acceleration of V over O. But then the key thing is that the acceleration of the velocity relative to the object is negative acceleration of the object relative to V. Manny, do you still have a question? Okay. Yep.
I had a question on problem 14.
Okay.
The angular velocity and the angular acceleration are both given as like 2.5 radians per second and negative 9.5 radians per second squared.
Mm-hmm.
But then when it was plugged into the like acceleration equation,
Mhm.
it switched to I think like positive 9.5 radians per second squared and negative 2.5 radians per second. Is that due to like the right hand rule or?
Let me just go through it. And the guy who does these problems sometimes makes mistakes.
Okay. I didn't know if it
I've
was
been trying to fire him.
or I did it wrong.
So let's at least set it up. So here's the carousel. And at the instant that we're thinking about, this will be the coordinate system. It has an angular speed of 2.5. So it appears, it doesn't say whether it's rotating clockwise or counterclockwise, so you can just choose whichever one. Let's say that it's the angular velocity is this way. So this is 2.5 radians per second. It's slowing down, so the angular acceleration is the other way. So that would be 9.5 radians per second squared. And so the way that I've drawn it here, my angular velocity would be, the right-hand rule says this is the positive y direction, so 0, 2.5, 0. And the angular acceleration is clockwise. Right-hand rule says that's the negative y direction, so 0, negative 9.5, 0.
Oh, so that's how it gets whether it's positive or negative.
Yeah, the right-hand rule, yes.
Oh, okay. I think it just I just chose the opposite.
That works too.
Clockwise or counterclockwise then.
Yep.
Okay.
Okay, let's go through number 15. This is the first gentle glimpse at what we're going to talk about first today. Okay, so until part C, this is just a circular motion problem. It has a radius of 5 meters. It has a clockwise angular velocity of 1.5. So let me draw that. So clockwise of 1.5 radians per second. And a clockwise angular acceleration, so it's speeding up, of 2.5 radians per second squared. And a passenger is in this position here. And if the center of the carousel is at rest, so here's basically, so what's the deal with the center being at rest or being moving or whatever? So let's think of the acceleration or velocity of the passenger relative to the ground. Okay. When it just asks for the acceleration and nothing else, it's asking relative to the ground. So this is equal to the acceleration of the passenger relative to the center of the carousel plus the acceleration of the center relative to the ground. Yep. The center is this, and yeah, you could imagine a camera that's there with the same orientation as whatever other camera.
When it's moving, like it's moving the same with the carousel.
Well, okay, so for parts A and B, it's not moving at all. It says that the center isn't accelerating. So that camera is just sitting there. Like that camera is fixed to the ground. There's no motion of the camera compared to the ground. Okay. You can imagine it's at the location of the center, but it's mounted to a separate pole that's just fixed to the ground. Okay, but that's going to change when we get to part C. Because in part C, it says, okay, what if that camera is moving, is accelerating? Okay, so in a way, I'm sort of setting it up right now so that to understand part C. But notice that for parts A and B, it says, okay, the center of the carousel is not moving. Okay, well, that means that the acceleration of the center relative to the ground is 0. Okay, and so all we're trying to calculate is the acceleration of the passenger relative to the center. Okay, that's because the center isn't moving. The center is the ground. Okay, so in that case, this is just a circular motion problem. So the velocity of the passenger is omega cross r. Omega is 1.5 in the negative z direction. Using the right-hand rule. And now r. Remember that r is the vector from the center of the circle or sphere to the object. And so in this case, that is, the radius is 5 meters. That's in the negative x direction. So this is negative 5, 0, 0.
Did you say that R vector can change sometimes? Like sometimes it's from the center to the point, and sometimes it's like.
Okay, the R vector always, its definition is from the center of the circle to the point. That's R always. And I think what I was talking about is when is R the same and when is it different from the position vector? Because that can get confusing. Well, they're the same when the center of the circle or sphere is the origin of the coordinate system. And a lot of times that'll just be where the coordinate system is located. And so a lot of times they will be the same, but you have to keep in mind that their definitions are different. And so it can, you have to figure out which one is which each time. In this case, they're the same because I put the origin at the center of the circular motion. Yes?
It's negative because of where the passenger is located?
Because it, R, yes, exactly. Exactly. So if this problem asked you, said the passenger was at the top, then this would be 0, positive 5, 0. Okay, so now we got these. Now we can calculate that velocity. So 0, 0, negative 1.5, crossed with negative 5, 0, 0. And that gives you 0, negative of negative 7.5, 0. So 0, 7.5, 0. And then it's always a good idea to sanity check your answers when you can tell what's going on. In this case, it's moving clockwise. So you'd expect the velocity at this point to be tangent to that circular path in the direction of motion. So it would be up. So that answer makes sense. And then we're going to do the same thing with acceleration. The acceleration equation is all ripe watermelons will rot. We already have omega and R. We just need to come up with an expression for alpha. Yeah.
So for the acceleration equation, do you want us to have that memorized, or can we just have that written down?
I do put that on the tests,
Okay.
but it's just sort of, it's kind of a nuisance to have to look through your notes every time you want to do one of these calculations. We're going to use that equation a lot of times. So, okay, so the only one we need is alpha. It's clockwise, which means that's in the negative z direction. So alpha is 0, 0, negative 2.5. Omega is what it was before, 0, 0, negative 1.5. And R is what it was before, negative 5, 0, 0. So the acceleration of P. Yeah.
The cross product. Oh, that's what I was. Like in the order of what I did the cross product.
Okay.
Sorry.
No problem. 0, 0, negative 2.5 crossed with negative 5, 0, 0. Plus 0, 0, negative 1.5 crossed with 0, 0, negative 1.5 crossed with negative 5, 0, 0. We already calculated omega cross R, so we know that this one is 0, 7.50. And now these two. So that is going to be in the x direction, and that is going to be 11.2500. And that's the centripetal acceleration. So does it make sense that that would be in the positive x direction? Yeah, the passenger's over here, so toward the center is in the positive x. And then this one, the tangential acceleration. So that is going to be 0, negative of negative 12.50. That's the tangential acceleration. Does it make sense that that would be up? Yes.
So you're saying you're breaking down which parts are like the centripetal and which parts are the tangential
Yeah.
acceleration? Is everything right of the addition sign the centripetal?
Yep, that's right.
Okay.
Yeah, if you remember the formula for centripetal acceleration from physics 1, it was omega squared r. So you can kind of squint your eyes at this vector thing and it makes sense that that would be the vector form of it, kind of. And so our final answer, the acceleration of P is equal to 11.25, 12.50.
Is that 11.25 not supposed to be?
Let's see. It's supposed to be positive. Remember that in the formula for cross product, the y has that extra negative in it. That's an easy thing to forget. The way in my head, I don't know, people do cross products on paper. The most common way is like this. Have you seen this before? If you write out I, J, K, and then write out the, so let's go 0, 0, negative 2.5, and then go negative 5, 0, 0. The cross product is the determinant of this. So if you cross out this row and cross out this row, now it's 0 times 0 minus 0 times negative 0.25. Then the rules for doing a determinant, this is where that negative comes in. Cross those two out. And you have a negative of 0 times 0 minus negative 5 times negative 2.5. So that's negative, positive, lots of negatives, and you end up with a positive. And then the last one, cross these out, and it's 0 times 0 minus negative 5 times 0. So 0, 12.5, 0. The way I think about it is I just think of the two next to each other like this: 0, 0, negative 2.5, cross negative 5, 0, 0. And I cross out that row and go this. Then I cross out this row and go negative of this times this, this times this. So you have to remember that negative again for the y. And then the last one is I cross out this and go this, this. Okay, so now part C. Yeah.
But then for the exam, we will have a calculator that.
Right. Yeah, just plug it into your calculator. Just people like things that you do all the time. People tend to like to have a way to do it in their head, Okay, so part C. So now it says now the center of the carousel. So all this old stuff is true still, but the center of the carousel has a given acceleration, 5, negative 3. Well, now what we have is that the acceleration of the passenger relative to the center, you can think of like this relative thing is like saying it's the acceleration of the passenger if you assume that the center is fixed to the ground. Okay, so this is just sort of a rewriting of what we already calculated. The acceleration of the passenger relative to the center is 11.25, 12.5, 0. And now we can use that in the relative motion equation. The acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the center plus the acceleration of the center relative to the ground. Yep.
But I thought that just got it was when the center wasn't moving, so it was like relative to the ground.
Yeah, well now, I mean, that's right. But we did it assuming that the center was not moving.
Yeah.
Okay. Well, you can think of that as the meaning of the relative motion thing. Like if you're calculating the motion of object A relative to object B, what you're doing is assuming that object B is not moving. Okay. So now we're going to say that the center is moving. And so we're still going to have, we already calculated the acceleration of the passenger relative to the center. But now the acceleration of the center relative to the ground is 5, -3, 0. So you get 16.25, -9.50. No. Any more questions about that one?
It was just confusing because, like, now that the center of the carousel moves with the passenger, like, wouldn't that be zero that they're both moving? Like, they're both on the carousel?
So I guess you can always think about these circular motion equations as giving you the velocity or acceleration of an object, assuming that the center of the circle or sphere, circular or spherical motion, is fixed. Okay, I think I didn't word it that way when I brought it up yesterday, but if you think about, like, when you think of a circular spherical motion, I think it's just kind of natural to imagine the center of that motion to be fixed to the ground. If the center of that motion isn't fixed to the ground, then what you're calculating is the velocity or acceleration of the object relative to the center. Okay, so that might be worth writing in here, I guess. I don't remember ever actually really describing it that way before, but that is definitely the way it works. So let's get it in here. So notice, the velocity, which is equal to omega cross r, is always the velocity of the particle relative to the center. And the acceleration, which is alpha cross r plus omega cross quantity omega cross r, is always the velocity, the acceleration of p relative to the center.
In a more general, because person and center are specific to the carousel, would it be velocity is always the velocity of the object relative to the vehicle? And the same is true of acceleration? It's always the object relative to the camera?
It's always the object relative to, so if you picture a camera that's fixed but not rotating at the center of the circle or the sphere, it's always relative to that camera. And so if that camera is accelerating like crazy, then you have to take that into account with relative motion. Yep.
So with this problem with saying the first part, the center is fixed, and the second part, the center is moving, is the center like just like a little ring that's rotating, or like the entire carousel like translating?
Yeah. So it's like, imagine that it's this Ferris wheel that first is fixed to the ground, and second, this is very dangerous. Don't make a carousel do this, but the second one is like it's on the back of a truck and it's still doing the same rotations, but at the same time that it's doing that, it's being carried around. Any other questions about that one?
Can you just go down so we can see the last part?
Yeah. Okay. I want to do two kinds of examples here. So the first one is just showing that you can use these relative motion equations with functions. So let's say that a cruise ship.
So this is still particle kinematics in our number.
Yeah. Yep. So a cruise ship sails as a passenger runs on the deck. A camera on the shore measures the ship's motion as the position of the ship is equal to 800 times the cosine of 0.001 t and 800 times the sine of 0.001 t.
So it's moving in a really big circle.
Really big circular arc. Yep, exactly. And then a camera on the ship measures the passenger motion as 30, so this is just a smaller circle, 30 times the cosine of 0.02 t, 30 times the sine of 0.02 t.
The person's angular velocity is also.
Right, because it's a much smaller circle. Yeah, right. I guess position of the passenger. And let's say we want to know what's the acceleration vector of the passenger. That's it. So, and when I don't give what it's relative to, I'm always saying the ground. Okay. So I'm going to say G is ground or shore. S is ship. P is passenger. And so our acceleration equation is going to say the acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the ship plus the acceleration of the ship relative to the ground. And so how do we come up with these? Well, we know that the position of the ship relative to the ground is 800 times the cosine of 0.001 t, 800 times the sine of 0.001 t. And so the velocity of the ship relative to the ground is the derivative of this. So that should be negative 0.8 sine of 0.001 t and positive 0.8 times the cosine of 0.001 t. And so the acceleration of the ship relative to the ground. How do we know that this makes mathematical sense, that we can just take these derivatives to get from position to velocity and what?
Yeah, yeah, respect to D.
Yeah, right. It's based on the definition, and that definition holds as long as the coordinate system is not rotating. These coordinate systems are accelerating, but they're not rotating. So this works perfectly fine.
But if it wasn't, T would even.
Yeah, or maybe you could use the chain rule. Maybe there'd be a way to use the chain rule. But okay, and then what's 0.8 times 0.001? So we got negative 0.0008 times the cosine of 0.001 t, negative 0.0008 times the sine of 0.001 t. Now, the position of the passenger relative to the ship is 30 times cosine of 0.02 t, 30 times the sine of 0.02 t. I'll just skip the first step and go right to the second derivative, but I'm just taking the time derivatives again. So this is 0.012, negative 0.012 times the cosine of 0.02 t, negative 0.012 times the sine of 0.02 t, and now it's just a matter of putting these together. The acceleration of the passenger relative to the ground is negative 0.0008 cosine of 0.001 t, negative 0.0008 times the sine of 0.001 t, plus negative 0.012 times the cosine of 0.02 t, negative 0.012 times the sine of 0.02 t. And there's your function for the person's acceleration. And now you could multiply by the mass and it would give you the net force on the person, stuff like that. You could start doing kinetics with that.
Could we go back to the formula, like, again, yeah, like, how do you know that the, the, the person on the, or the passenger on the ship, like, I'm just now like a little confused, because like the person is like on the ship,
Mhm.
so they don't move like the same, like only one acceleration, they don't be zero.
Well, so think of it like this. So there's always going to be a ground, and there's always going to be some implied camera fixed to the ground. Okay. In this case, that's described as the camera on the shore. Okay. Then there's always going to be some kind of intermediate thing, a vehicle or something, that also has a camera fixed to it. Sometimes that's described and sometimes it's not. But in this case, the camera on the ship is the camera that's fixed to the vehicle, the intermediate thing. and then both of these two things have the ability to, to observe the object of some thing. In this case, it's the passenger. And so I just always put these things in this order. And then I'm just reading the text to see the values that it gives us. What's it referring to? Like, is it talking about a camera fixed to the ground, a camera fixed to the vehicle?
So with these types of problems, we're never considering like the camera as one of the points. It's always like ground, vehicle, objects like person.
Well, actually, I mean, I guess in a way you're always thinking of like in this second term on the right side, you are kind of thinking of the vehicle as the thing that you're tracking from the ground. So really you should think of the thing that's moving and the vehicle and the ground, they all have coordinate systems attached to them, and you can measure any of the other ones from any of those coordinate systems. It would be a little weird to measure the motion of the ground relative to the passenger, say. Like, you don't really think of it that way as like a person holding a camera measuring the motion of the shore. But that's a perfectly valid thing to do. You could do that. We just don't tend to think that way. Any other questions about that one? Okay, so now we're going to do something that is going to come up a lot. So now we're going to combine circular and spherical motion with relative motion for linkages. Yeah, and then if you wanted to know the acceleration at a single instant, you could plug in a value at time. Okay, so now it's going to be our first look at linkages. We're going to spend a lot of time on linkages when we're doing kinetics of rigid bodies. And the idea with linkages is that we're going to be combining circular and spherical motion with relative motion. Okay, so I'm going to show this as an example. So let's say that we have a hinge connected to the wall and a first body like that, and then another hinge connecting that bar to this bar. Let's say this makes an angle of 30 degrees with the horizontal. The second one is horizontal. Let's say, stupid computer. Let's say this is the point P that we're going to try to calculate something for. Each of these members is 1 meter long. And let's say that this first body has an angular velocity counterclockwise of 10 radians per second. And an angular acceleration of 5 radians per second squared. And the second one has an angular velocity this way of 8 radians per second. And an angular acceleration of 20 radians per second squared. And we want to calculate the acceleration of that point P relative to ground. Relative to ground is implied if we're not tell you something about what it's relative to. Okay, the first thing, this is kind of a new concern, but notice, so what do the angular velocity and angular acceleration mean? So omega and alpha are rotations relative to a non-rotating implied thing. Non-rotate, that's too many tatings. Rotating relative to fixed. So you might, you might have the tendency to think that that these are telling you how this body is rotating compared to this one, but that's not what it means.
I mean, how it's rotating relative to the pin attached to the wall.
Yeah. Yep. And so, if these were exactly the same, if this one was 10 and 5, this thing would just be rotating like a rigid body. Okay. That the angle between them wouldn't be changing at all.
Like rods, is it like frictionless? So if nothing was happening, they would both like fall down.
Well, we're not doing kinetics yet. I mean, that is the idea, yeah. But I guess really it doesn't matter yet since we're still just doing kinematics. But when we start doing kinetics, yeah, we're going to assume that it's frictionless. Yep.
So one rod spinning doesn't affect the other rod at all.
I mean, it might affect it, like how it affects it. We have to do the force calculations to see that. But in describing it with the angular velocities and angular accelerations, those are totally independent numbers. Yep.
When you say it's rotating, do you mean it's rotating this way?
Nope, in the plane.
Oh,
Yeah. And all the linkages stuff we're going to do is going to be motion in the plane. Okay, so I'm going to call this pin connected to the wall the ground. And I'm going to call the pin connecting the two bodies A. I'm just giving them names. And what I'm going to do is use relative motion to say the acceleration of P relative to the ground, which is what we want, is equal to the acceleration of P relative to A plus the acceleration of A relative to the ground. And so the way this works is the acceleration of A relative to the ground is just the circular motion of this point around the pin. Okay. And the acceleration of P relative to A, that's another way of saying, forget for a second about any motion of the center. Calculate the circular motion of this point, assuming that that's fixed. And then we'll put them together to give the total acceleration of the point P. Yeah.
So even though like the point A might be moving through space, we're assuming it's fixed?
Only for this part.
Okay.
Like that's what it means to calculate something relative to A, is we're going to assume that A is fixed. Okay, so first I'll do the acceleration of A relative to the ground. And and that's equal to all ripe watermelons will rot. And now we can just write down these values. So R is the vector that goes from the center of the circular motion to the point we care about. In this case, the center of the circular motion is G, and the point we care about is A. So that R is going to be 1 times the cosine of negative 30, 1 times the sine of negative 30, so that's 0.866, negative 0.50. And then omega is, so we're talking about the motion of that diagonal member. So that's a counterclockwise 10 about the, and I'm going to use our usual coordinate system with z coming out towards us. So counterclockwise is positive z. So this is 0, 0, 10. And the angular acceleration is also counterclockwise. So 0, 0, 5.
Where are you seeing the counterclockwise?
I just drew the directions of those arrows. Yeah, both of those arrows are counterclockwise. And then when we get to the next body, the angular velocity will be clockwise and the angular acceleration will be counterclockwise. Okay, so acceleration of A relative to G is equal to 0, 0, 5 crossed with 0.866, 0.50.
-0.5.
Yep, thank you. Plus 0, 0, 10 crossed with the quantity 0, 0, 10 cross 0.866, negative 0.50. And I'm just going to plug this into my calculator. So I got negative 84.1 positive 54.33 0. And now we have to calculate the acceleration of P relative to A. So again, we're going to use the acceleration equation, all ripe watermelons will rot. And we need to use the new body. Now we're assuming that since this is relative to A, now we're assuming that A is fixed, and we're just calculating the acceleration of P due to the circular motion of this second horizontal body. So R this time is 1, 0, 0. Omega this time is 0, 0, negative 8. Yep.
You said that the angular velocity and angular acceleration were relative to the ground, not relative to A.
Right.
So now we're trying to find it relative to A. Don't we need the angular acceleration relative to A?
No, angular quantities are always measured compared to some absolute, somewhere out in the galaxy or out in the universe somewhere is an object with no rotation, and that's what we're comparing it to. Okay, so now the acceleration of P relative to A is equal to 0, 0, 20 crossed with 1, 0, 0 plus 0, 0, negative 8 crossed with quantity 0, 0, negative 8 crossed with 1, 0, 0. So 0, negative 8, 0. And then 0, 0, no. This one is negative 64, 0, 0. And this one is 0, 20, 0. And so when you add those two terms together, you get negative 64, 20, 0. Yes.
I'm confused about the angular acceleration and velocity values.
Okay.
You said that they were relative to like an outside plane, but we're measuring with respect to A. So I thought we would have to like combine some values from the way that A is moving to get.
So when I say, that was,
It might have been the same question.
yeah, I think it's the same confusion. So what we're calculating is a translational acceleration of that point P, assuming that that point at A doesn't move. Okay? But in order to do that, we have to use those absolute angular quantities.
I'll work on it.
I know it's confusing. Yeah.
And I think the last step is we add this quantity of the acceleration at point A to the acceleration at point B.
Yes,
Okay.
exactly. That's the last step. Question?
When I do the right hand rule for like your W, it makes me want to think it goes in the positive X.
Okay, let's see. For which ones?
So like your W between like P and A.
Okay. Well, for the z-axis is coming out. If you do that, your thumb is going into the page.
Oh, okay. So I have to actually. But when I do this, you think when you do the 8,
Mhm.
don't you just get this?
And that's into the page.
That's just the way I'm holding it. I need to be holding it like this.
Yeah.
I'm looking at the paper. Okay.
Oh, yeah. Well,
That's the way I'm
right.
holding it.
Right. But if you do that, your thumb is into the page. So that's negative z. You do this, your thumb is out of the page. So that's positive z.
So what would it give you if, like, for it to give you like positive X? Like, how would the drawing have to be like there?
Well, to answer that, put your thumb in the direction of positive x, and then your fingers would have to curl this way out of the plane.
I feel like that's how 8 is currently.
That's what I was thinking too.
Like that's, yeah.
Oh, well, these are all supposed to be, these rotations are all supposed to be living in the page, you know? So nothing's going out of the plane or anything. These things, all they can do is rotate in the page.
So like this E coordinate, like is coming from that joint.
Out.
So then everything else is like on the X, like.
Yeah. Everything else is in the XY plane. Everything that's happening is in the XY plane.
Is it always going to be like that for the most part?
Yeah.
Okay.
Actually, I think there might be one or two problems where I make you do it in the XZ plane or something, but just to try to make sense out of the directions. Let me just finish this real quick, so you have it in your notes. So the last part is now we're just adding this up. So the acceleration of P relative to the ground is negative 64.20 plus negative 84.1 positive 54.330. And so the total acceleration of that point P, the one you could use in Newton's laws, is negative 148.1, 74.330. And so now if there was some, electronics or something you were worried about at this point P, in this, for some reason, this is the way your machine works or whatever, and the mass of that, you could figure out, multiply the mass to this acceleration and it would give you the net force that has to be applied to that thing.
Would that be over the whole rod or just at the?
Just right at that point. Yep. Right at P. Any other questions about that, or want to go back and revisit some of these? Okay.
I think the misunderstanding is how it's like the planes you're talking about.
Yeah.
I think that's what makes the big difference.
Okay. Yeah. Well, remember that. So our hands are useful for a lot of things, and so I'm not mad that they weren't designed that great for the right hand rule. They do a lot of things really well, but really, just for physics, it would be better if your hands were like this: a disc, with a arrow drawn on them, and then an arrow pointing straight out like this. So that's really what the right hand rule is getting at. It's relating a rotation in one plane to a perpendicular arrow, And so like this, you could 3D print like a pendant or whatever like this, and then you'd never have to think about the right hand rule. You could just hold your pendant up to the page.
A spinning top.
Yeah.
Spin it.
That's true.
And it has like an arrow.
That's true, as long as you spin it with the correct hand.
So like the drawing that you have up there, with the two rods and the point, that's drawn in 3D.
This is drawn in 2D. Everything there is happening in the page. And so, like, you would take this pendant and flip it over so that this circular motion lined up with this, for example. And the arrow part of it would be pointing straight out of the page.
No, it's actually going left.
There's one that.
Yeah, it's okay this way.
Okay, hold on. How much time do we have? Okay, hold on. I'm going to make this thing.
Because it's going in a counterclockwise direction. It's going out.
Okay. Here. So here's the pendant thing. Okay. So here it is. And so I'm going to go up to this. And which one of these rotations do you want to do that?
220.
The 20. Okay. So I'm going to hold this so that this rotation represents the rotation for the 20, like it is now. And the arrow is pointing out of the page in the positive z direction. So that's 0, 0, 20.
Isn't that just the acceleration, not the direction?
What?
Rats s squared?
That is the direction of the angular acceleration.
Okay.
And now let's do 8. Okay, so this time, those are not in the same direction, right? So I have to flip it around backwards. Now the arrow is in the same direction as the 8.
But the tail is pointing out towards us, but the tip is going
The-
into the page.
Right, but the arrow is pointing into the page.
Isn't there like a notation for that or something like a dot versus
Yeah.
cross? Like I think it was
Yeah.
like physics 2 or something, right?
Yeah, right.
When we were talking about current or something, or
Yeah. Mhm.
and
Magnetic fields and all that
magnetic
stuff.
fields, yeah, exactly.
Instead of wrapping around the page, invoking.
And it's mainly just clockwise versus counterclockwise, right hand rule, your hands curl in a clockwise direction, counterclockwise direction. And
Yeah, physics 2 is where people
this
would have
is
done
the
most
clockwise
of this stuff, and I know not all of you have taken physics 2, but, okay. Who wants to keep this pending?
maybe
Okay.
a 3D project.
Yeah, we
3D
should
printer
3D
project.
print them in engineering design, good for dynamic.
Also, like just the other 3D right-handed rule where you use like 3 axes, right?
Yeah.
Which is like y-axis to the plane and then middle finger is the z.
Yeah, yeah,
Or it kind of works either as long as you have line two axes, right?
yeah.
It also just kind of looks like you're